Let's consider some of the ways that we actually analyze time series and begin to understand them. I'm going to begin by introducing you briefly to something that is one of the most potent, powerful, and useful methods of time series analysis known to humanity. The combination of the human eye and the human brain is one of the most potent pattern recognition systems known. That's why a first step in time series analysis, unfortunately one which is too often neglected, is make a graph of the data and look at it. In fact, you could make lots of graphs. Look at small sections of the data or large sections at different scales. This may not seem like a very scientific thing to do, but it actually is. There's even a scientific name for this. It's called visual inspection. Don't underestimate its power. It's one of the best ways to get ideas about what might be happening. You'll also find that the more you study time series and the more graphs you make and look at, the better you'll get at it. The better you'll get at being able to determine the difference between what's real and what's imaginary. There is, by the way, a very important danger with relying on visual inspection. It's not always right. The eye plus brain combination is all too easily fooled. We're far too likely to see patterns or processes which are really just noise. It's like seeing pictures in the clouds that aren't real, they just spark our imagination. Our ability to look at a jumble of randomness and imagine that we can see the Mona Lisa or the Sistine Chapel is downright impressive. But it's just a jumble of randomness. It's just pictures in the clouds. So don't neglect visual inspection. It's too potent to ignore. It really is one of the best ways to get ideas about what might be happening. But do be skeptical about what you see might be there, and be prepared to back up any ideas you get with actual mathematical analysis, so you can say reliably whether they are real patterns or whether it's just something that seemed to be that way. Now, we want to take a time series and understand it, and one of the most important things is to break it into its pieces that go together to make it up. The one most fundamental decomposition of a time series is into the two primary parts. Now, some time series are completely random. For instance, flipping a coin. It's completely random if the coin is fair. There's no signal there. There's no deterministic part. There's nothing changing over time in any perfectly predictable way. It's just random. Time series can also be completely deterministic. For instance, the path of a spacecraft through empty space can be determined ahead of time because we apply the laws of physics, and that allows us to calculate what is going to be in the future. There's not really any randomness involved. I suppose there perhaps is at the quantum level, but we're not going to get that fussy. Now, those are two extreme cases, one completely deterministic, the other completely random, something we would refer to as stochastic. But it's much more common that a time series is a combination of both. It has a deterministic part, and it has a random part. The deterministic part is often called the signal, at least that's how I usually refer to it. The random part, called the stochastic part, is sometimes called the noise. So the main decomposition of a time series is into its deterministic and stochastic parts, into the signal and the noise. By the way, there's a particular kind of noise you ought to be aware of, and that is something called measurement error. A physical process, we might find that it's perfectly, completely deterministic. But when we observe it and measure it, we also find that our measurement apparatus is not perfect. So that, for instance, consider the brightness of a star. That can be measured. It's usually measured on a scale called magnitude. And if the star is perfectly constant, its magnitude will be perfectly constant, which would be a rather boring time series because it would never change. But when we measure the brightness, our measurements are bound to be imperfect. The difference between the brightness of the actual star and what we measured it or estimated it to be is called the measurement error. We hope it's random. Now, not all processes that are random are measurement error. Some are, but the process itself can include randomness. For example, the coin flip. Processes can also be effectively random. For instance, suppose you measure the amount of rain that falls in your backyard every day. You might find that there looks like there's a lot of randomness in it. Now, if we knew the laws of physics perfectly and we had infinite computing power, which we don't, we might be able to predict perfectly how much rain was going to fall for the next 2 weeks or 2 months or who knows how long. But the weather is chaotic. That means that a small, tiny change in starting conditions can lead to a huge change in ending conditions. So we're never going to be able to predict it with the perfection that the laws of physics might dictate. The process is chaotic, and therefore, if we observe it, it looks effectively as though it's random. So there can be a lot of randomness in stuff that we observe because its underlying physics is chaotic, and so it behaves as though it were random. It's also important to note that there are processes that we can observe and measure that have genuine, true randomness in it, not just because of chaos and not because of measurement error, but actual stochastic behavior in the time series. And we want to break a time series apart into, let's say, stochastic and deterministic parts, signal and noise. But then there are many ways that those two components can combine to form the time series. The most common way by far is what's called the additive model. That's where the data that we observe is equal to the signal, the deterministic part, plus the noise, the stochastic part. X is equal to F plus epsilon. X, the data, is F, the signal, plus epsilon, the noise. This is the simplest way to decompose time series. It's also the most common. By the way, separating into signal and noise isn't the only decomposition that we probably want to carry out. The signal itself, the deterministic part, we might be able to decompose that into important different pieces. For instance, we might find that some part of it is periodic. It's a cycle or seasonality, and that there's also a non-periodic part that we might call the trend. And to combine those into the signal, we might use an additive model again, so that the signal, F, is equal to the trend, capital T, plus the seasonality, capital S. So we can decompose a time series into signal and noise. We can decompose the signal into trend and seasonality or periodic behavior. By the way, sometimes, especially in time series for economics, they will further decompose the periodic part into the part that is truly seasonal, having to do with the year, month, whatever cycles are imposed by the calendar, and longer term cycles that aren't always perfectly cyclic or periodic, that they generally refer to as cyclic. I'm not going to do that. I'm more interested in physical science. So, but bear in mind that economics approach to time series can be somewhat different from the approach I'm taking. By the way, when we combine different pieces, we combine signal and noise into data, or when we combine trend and seasonality into signal, the additive model isn't the only model. We might say, for instance, that the signal is equal to the trend times the seasonality. That would give us a multiplicative model. We could even say that the signal is equal to the trend raised to the power of the seasonality, an exponential model. In general, we can combine them in any way. We can say that the signal is any arbitrary function of the trend function and the seasonality function. The only limit to how you can combine terms is your imagination. And that goes for both signal, breaking down into trend and seasonality, and data breaking down into signal and noise. Do be aware, though, that the additive model is the most common way it's done, and one of the most common ways that it actually happens in nature. Sometimes we want to mix and match. For example, maybe the signal is a multiplicative combination of trend and seasonality, but the time series itself is an additive model of signal and noise, in which case X, the data, would be equal to capital T, the trend, times capital S, the seasonality, plus epsilon, the noise. The most generic combination would be that X, the data, is some general function of a trend function, a seasonality function, and a noise function. The general principle when you're trying to understand how to decompose things is that simplicity often works the best. For one thing, things often combine in a simple way. And for another thing, we may not always be able to define more complex models as precisely as we can a simpler model. So a simpler model is usually our best chance to get a model that is actually good enough, a close enough approximation to reality to be genuinely useful